Understanding normal distribution, a comprehensive guide. Normal distribution, frequently referred to as the Gaussian distribution, is a cornerstone concept in statistics and probability theory. It plays a crucial role not only in theoretical mathematics but also in applied fields such as finance, psychology, and natural sciences. This article delves into the fundamentals of normal distribution, its properties, applications, and limitations. What is a normal distribution? A normal distribution is characterized by its symmetric bell curve shape, wherein most data points cluster around the central peak, and probabilities for values further from the mean taper off equally in both directions. In mathematical terms, when data are normally distributed, mean, mu the average of the dataset, where the peak of the curve lies. Standard deviation, sigma a measure of the data spread around the mean, affecting the width of the curve. In standard normal distribution, the mean is set to 0, and the standard deviation is set to 1, resulting in a specific representation on the graph. Key features of normal distribution. 1. Symmetry. The distribution is symmetric around its mean, which means that the left side of the curve is a mirror image of the right side. 2. Equal measures. In a normal distribution, the mean, median, and mode are all equal, located at the center of the curve. 3. Empirical rule. 68-95-99.7 rule. This rule outlines the percentage of observations within standard deviations from the mean. About 68% of the data falls within one standard deviation, plus or minus 1 sigma. About 95% of the data falls within 2 standard deviations, plus or minus 2 sigma. About 99.7% of the data falls within 3 standard deviations, plus or minus 3 sigma. Understanding skewness and kurtosis. 1. Skewness. This term evaluates the asymmetry of the distribution. A skewness of 0 indicates perfect symmetry, normal distribution. Negative skewness means the left tail is longer, left skewed. Positive skewness signifies a longer right tail, right skewed. 2. Kurtosis. This measures the tailedness of the distribution. A kurtosis of 3 indicates a normal distribution. Leptokurtic, kurtosis of 3 indicates fat tails, suggesting that extreme values are more common than in a normal distribution. Platykurtic, kurtosis E3 indicates thinner tails, suggesting extreme values are less common. The formula of normal distribution. The probability density function of a normal distribution is expressed mathematically as \fx equals \frac 1 \sqrt 2 \pi \sigma 2 frac x mu 2 sigma 2 where \fx is the probability density function. \x is the variable. \mu is the mean. \sigma is the standard deviation. Applications of normal distribution in finance. In finance, the assumption of normality is pervasive. It aids in the evaluation of asset prices and their movements. Price action analysis. Traders often desire to plot historical price data to determine how it fits a normal distribution. Significant deviations can indicate overbought or oversold conditions. Risk management. The normal distribution helps in calculating value at risk, VAR, an essential tool in risk management to estimate the potential loss in value of a portfolio. Statistical modeling. Numerous statistical methodologies assume that asset prices follow a normal distribution, which is foundational for various financial theories and models. Limitations in financial applications. Despite its broad applicability, normal distribution has notable limitations. Non-normal returns. Financial returns often exhibit skewness and kurtosis, implying they do not follow a pure normal distribution. Real market returns demonstrate fat tails, indicating a higher probability of extreme events compared to a normal distribution. Inaccurate predictions, relying solely on the normal distribution, may lead to misleading conclusions, particularly during volatile market conditions or when predicting extreme events, e.g., stock market crashes. Real-life example of normal distribution. Many natural and social phenomena are examples of normal distribution. For instance, human height is often perceived as normally distributed within a population. If we consider a population where the average height is 175 centimeters, roughly following the empirical rule, about 68% of people will range between 169 centimeters and 181 centimeters, plus or minus 1 sigma. About 95% will range from 163 centimeters to 187 centimeters, plus or minus 2 sigma. About 99.7% will fall within 157 centimeters to 193 centimeters, plus or minus 3 sigma. Historical context. The term normal distribution emerged in the 19th century, primarily from the work of mathematicians like Carl Friedrich Gauss, who initially described it in the context of measurement errors. The popularization of the term can be traced back to Sir Francis Galton's work on natural inheritance, where he remarked about the normal variability observed in various data. Conclusion. The normal distribution remains a foundational component of statistics and finance, providing tools for understanding data and making informed decisions. However, it is crucial to recognize its limitations, especially in complex scenarios inherent in real-world data. Awareness of these nuances allows for better application and more accurate interpretations of statistical outcomes in a variety of fields.